Okay, so thank you very much for the introduction, and I'd like to thank the organisers of the workshop for the invitation to speak, and also the organisers of the semester programming analytic number theory. So I've been fortunate to be here since January, and some of the work I'm going to talk about today has been done during my stay. Okay, so as you heard, the talk is about better than square root cancellation for multiplicative functions. And I'm going to focus on a specific kind of multiplicative function, which is Dirichlet characters. But the methods apply a bit more generally than that. So if people are interested in that, they can ask later. And the plan of the talk, so first of all, there'll be an introduction. And I'll talk about square root cancellation a bit and state some results. And the results will be of two kinds. So there'll be results in a sort of random model problem. So how does a typical multiplicative function behave? And so in the second part of the talk, I want to say something about the ideas of the proof in the random case. And then it turns out that you can use the results of the random case to deduce things in some deterministic settings as well. So the third part of the talk is going to be, hope to say a little bit about proof ideas in the deterministic case. So maybe I should check at this point, is that visible at the back? Okay. Right. So I want to start with a very straightforward problem, hopefully. So I'm going to let R be a large prime, because P and Q will be used for other things later. And X somewhere between 1 and strictly less than R, let's say. And then I want to look at the sum of a Dirichlet character chi over all n less than x, and I'll square this and average on the character. So sum over all the characters chi mod R, and R is prime, so there are R minus 1 of those. And I'd like to know how big this is. And of course, we can do that. So I can expand out the square, so this is the sum over n1, n2 less than x, and then I'll move this sum to the inside. Sum over chi of n1, chi of n2 conjugate. And now by orthogonality, the only terms that survive here are the ones where n1 is congruent to n2 mod r. And since everything is smaller than r, the only way that can happen is if n1 and n2 are actually the same. So the only terms that survive are the diagonal terms. So this is just the floor, the integer part of x. Okay, so I hope this is uncontroversial so far. Right, so I'll make two remarks about this. So first of all, I had the principal character in the sum. I needed that to get the perfect orthogonality. But unless x is really big, it doesn't matter really whether the principal character is there or not. So provided x is smaller than, let's say, 0.99, r minus 1, the principal character doesn't dominate. And in fact, you can see, so the contribution of the principal character, well, it's 4x squared, but there's only one principal character, so we divide by r minus 1. And then under this condition, this is at most 0.99 floor of x. Okay, so I can remove 0.99 floor of x from floor of x and not change the order of magnitude of the answer. So for most of the things I'm going to say, you can put the principal character in or take it out if you want. It doesn't make any difference. Now the other thing is, I think I labeled that star. So star is consistent with all, or at least many, of the sums satisfying that the sum is about square root x in size. Okay, so if they were all root floor of x, then that's exactly the answer that you would get. We know there's at least one where that isn't true because the principal character is in the sum. But if at least many of them were about this size and not many of them were too much bigger, you get the answer in star. And this is square root cancellation. Because the trivial bound here is x, and we're getting behavior that's consistent with things being about square root of a trivial bound. Okay. So what I want to talk about for most of the talk is just a small variation of that question, which, however, turns out to be much more interesting. So that's the second moment, or the L2 norm squared of the character sum. So I want to ask what happens to the L1 norm. So what about the L1 norm? So 1 over r minus 1, sum over chi, the absolute value of the character sum, but without the square. Right. So if you see this, I think there's precisely one thing that's obvious to do, which is you can apply Cauchy-Schwarz to get back to the L2 norm. So by Cauchy-Schwarz, this is at most the square root second moment, so that's square root floor of x. And what I want to know is that sharp or not, in order of magnitude. So if it's sharp, I'd like a lower bound for the L1 norm of the same size. And if it's not sharp, I'd like to improve the upper bound. Right. So there are questions about what I said so far? Okay. So what I'm going to do now is I'm going to hedge my bet a little bit. So first of all, I'm going to give some reasons why you might think that that should be sharp. And then I'm going to give some reasons why you might think it's not. And then I'll state some theorems. Okay, well, one excellent reason for thinking it's sharp is that it actually is sharp on a certain range of x. So it is sharp. When x is between 0.01r and 0.99r, let's say. Now, why is that? Well, there's a result of Montgomery and Vaughan, I think from 1979. Yeah. Which says the following. So here I do have to exclude the principal character from the sum. So now there are r minus 2 things there, so for aesthetic reasons, I'll divide by r minus 2, but it doesn't make any difference. And what they do, so they look at the sum of the character to the power 2q, and they can upper bound this by some constant that depends on q times r to the q. And they can do this for any q. So what you should observe here is that the bound doesn't get better as x gets smaller, which is what you should expect is probably the real behavior. So it's a bound just in terms of r, not in terms of x. But on the other hand, they have this for all q. And for people who know about these things, they actually prove a stronger result than this because they don't just have to have a fixed sum here. For each character, they can take the maximum character sum and still get r to the q as a bound. Right, so in particular, so I want to take q to be 2 and be on that range. So when x so when x is like that, we get that the fourth moment is at most, well, it's at most r squared, but r and x are comparable in size, so that's the same as at most x squared. Okay, so by Holder, combining this with the L2 result that I called star somewhere there. So combine this with star gives a lower bound. Actually, I guess it gives a lower bound for this. So the sum over chi n equal to chi naught, absolute value, sum of chi of n is greater than root x. Okay, so this is just a little calculation that you can do, but if you're not used to this, I can maybe say qualitatively what's going on here. So the lower bound, or even the equality that we have for the second moment, is consistent with all the things being of size about root x. But what could be happening is that there could be a few that are really big that are pushing up the size, and all the rest are small. But if that happened, then when you took a higher moment, so the fourth one, the really big ones would get even really bigger. So they would inflate the size of the higher moment, and they don't, because we have the estimate over there. So if you know that the high moment is consistent with, as an upper bound, with all the things being of size like root x, and the low moment as a lower bound, or even an equality is consistent with them all being of size root x, then actually many of them must actually be of size root x. Okay, so this is a straightforward-ish calculation, but also qualitatively, hopefully it's fairly clear what's going on here. Okay. So that's one reason to think that maybe square root x is the correct answer. Now, another reason is a sort of wafflier reason. So philosophically, when people talk about square root cancellation, what they often say is that square root cancellation is like like what happens in the central limit theorem. Okay, so why should you get square root cancellation? It's because everything is kind of random. It's like the central limit theorem. Right. Now, if it really were like the central limit theorem, so like a Gaussian, now for a Gaussian, all of the L2Q norms, so if you took the 2qth moment and then took the 1 over 2qth power, all of those are of the order of magnitude of the standard deviation. So in this case, order root x. So for a Gaussian, all the L2Q norms would be the order depending on q of square root x. Okay, and what I sort of vaguely claim is that maybe most analytic number theorists, if you asked a random analytic number theorist, they might say that square root x is probably the correct answer in this problem. So I guess I could try and find a suitably random-looking analytic number theorist in the audience to ask, but I won't do that. But I think square root x, it's a natural default guess, at least, what the answer is. Okay, so now reasons to think square root x isn't sharp. Right, so one thing you could do is you could look at a random model for the problem. So here's a random model. So I'm going to let f of p for p prime be independent random variables each one uniformly distributed on the unit circle in the complex plane. And this distribution, this is called the Steinhaus distribution sometimes. Right, so now I'm going to define f of n to be the product of f of p to the power a, where p to the a is the highest power of p that divides a. Okay, and this is something that people study, and this is called a Steinhaus random multiplicative function. Okay, so it's a Steinhaus random function because it's built from these Steinhaus random variables. And it's multiplicative because you can see that the value n is built multiplicatively from the values at all primes. And actually, it's totally multiplicative, just like a Dirichlet character is totally multiplicative. And in this setting, there's a conjecture of Helson from 2010, which is that if you look at the L1 norm, so here the L1 norm is just this expectation of the absolute value, This should be little o of square root x as x tends to infinity. Okay. Now, wasn't known how to go about proving this. No upper bounds were known that were better than square root x. There were some lower bounds. So there were lower bounds of Helsing himself, or following from his work, and of Bondarenko and Sipe, and of myself and Bali and Radziwill. And we showed that the expectation is at least as big as root x over log x cubed, roughly. So if the conjecture is true, it's at least not very true. It can't be too much smaller than root x. But nothing was known about how to maybe prove this, but at least in this setting there was a conjecture that it should be little o of square root x. And I should say as well, why did Helsing think this? Well, maybe this is analogous to the following. So what I'm doing there is I'm taking a multiplicative character, a random character, and summing up to some point, and taking the L1 norm. And what he suggested is maybe this is analogous to taking an additive character and summing up to some point and taking the L1 norm. And if it is, then this is the L1 norm of the Dirichlet kernel, so this is actually really small. This is maybe like log x in size. So in this setting, it's definitely true that the thing is the lower root x. It's not clear that that should motivate you to believe the conjecture, but anyway, that's a reason. And I'll state one more reason why you might think that square root x isn't sharp. So what we've been doing here is we've been looking at a problem on the 0 line. Okay, so we've taken the coefficients of an L function and Dirichlet L function and summed them up without any weights. And what you could think about is what goes on the 1/2 line instead. So I can look at 1 over r minus 1, the sum over chi mod r, L1/2 chi in absolute value, which roughly speaking is the same as 1 over r minus 1, the sum over chi mod r, the sum over n up to about r, chi of n over square root n. Okay, and now, so if what were going on was square root cancellation, then what you would expect is that this should be like the square root of the sum of the squares. So this should be like square root sum over n less than r, 1 over n, which is like square root log r. Size. Okay, so square root cancellation would suggest that's the answer, but that's not the answer. So actually, is order log r to the power 1/4. And this is a result of Rudnick and Sandarajan for the lower bound, and of Heath-Brown for the upper bound. Okay, so on the 1/2 line, at the critical point, you get better than square root cancellation. And why is that? Okay, I stand corrected. Thank you. Right, so why is it smaller? So this is because of the role of the Euler product. Okay, so on the 1/2 line, even though the Euler product certainly doesn't converge anymore, it still has a big influence on the behavior of the L function. And the Euler product causes a sort of collapse. So you have a collapse in the size to the Euler product, which gives you this size for the small moments. So you can think about the question, do we have square root x or better than square root x for the L1 norm of the character sum as being a question, does the influence of the Euler product extend even out to the 0 line or not? Right. So now I will put you out of your suspense or misery, such as it was. Right, and state some theorems. So theorem 1 is in the random setting, so that f be a Steinhaus random multiplicative function. And q between 0 and strictly less than 1. Then if I take the 2qth moment here, this is of the order of magnitude, depending on q, x over square root log x to the q. So this means it's at most some constant, depending on q times this, and it's at least some other constant, depending on q times this quantity. Right, so in particular, if you take q equals 1/2, then you get that the L1 norm is like square root x over log x to the 1/4. So the conjecture of Helsing is correct. It is little o of square root x, so x tends to infinity. Okay, so now you could ask, so what does this mean for the character sum problem? So maybe this means that for the character sum problem, you should have better than square root cancellation as well. Or maybe the random model is just failing to capture the arithmetic in the character sum problem properly. And we know that has to be the case to some extent because I already showed you that for a certain range of x, when x is order r, essentially, you do have square root cancellation and not better than square root cancellation. But it turns out that that's essentially the only case where you don't have better than square root cancellation. So this is theorem 2, so let R be a large prime. And x between 1 and R, like before. I'm going to set L to be the minimum of x and R over x. And then for any q bigger than 0 and strictly less than 1, we get an upper bound. Actually, it doesn't matter. So it's not chi mod r. q is less than, depending on q, x over the minimum of square root log L and square root log R to the q. So provided that x tends to infinity and r over x tends to infinity, the denominator tends to infinity. And so you have a better than square root saving here. Okay, so probably the second term, so the square root log R can be removed. And this is work in progress to do that. I think it can be, but I haven't checked all the details yet. And if it were removed, then presumably in view of theorem 1, that would be a sharp upper bound. So if you don't immediately see why L should come into things, I'll explain that in the last part of the talk when I say a little bit about the proof. But maybe if you've worked on these things before, it's reasonably clear. There should be some symmetry between x and r over x. Right. So that's the end of the introduction. So there are questions before I go on and talk about the proofs.
This expectation of square root cancellation in the chi of PQ is not independent of chi P and chi Q. So what do you expect that? So you treat them as
Here?
each ends are independent, but you have this multiplicative structure.
So if so another way of saying that would be if you apply Cauchy-Schwarz to get to the second moment and just expand out and use orthogonality, that's what you get. That's the answer. So the second moment is like log R. So if you do Cauchy-Schwarz, you get square root log R as a bound for the first moment.
That's when like each coordinate is independent.
No, for the character you get this by orthogonality.
For the square.
Yes. So what I'm saying is that the Cauchy-Schwarz band, which uses the orthogonality, so that the second moment comes from orthogonality, the same for the characters as for the random case. And what I'm saying is that the Cauchy-Schwarz to the second moment band is incorrect for the first moment of 1/2 chi. And it's also incorrect, although not as much, for the character sum as well. Thank you. Other questions? So I want to say a bit about the proofs. So the proofs are quite complicated. So I'm not going to give even a sort of detailed sketch of how they work. What I want to do instead is to just identify some of the issues that come up and how you might start to think about trying to solve the problem. So first of all, I'm only going to talk about the upper bound. So I'm talking about the random case here, so theorem 1. And the first sort of idea or theme, so theme 1, I want to connect this thing I'm trying to bound to the Euler product, which in this case is a random Euler product. F of S, so the product over primes less than x, 1 minus f of b, p to the s to the minus 1. Why do I want to do that? Well, actually, there are lots of reasons. So first of all, it's the only clear hope of handling the case, which here is the only case I'm interested in, where 2q isn't twice a natural number. Okay, if the exponent is twice a natural number, I can expand the square, hope to do something. If the exponent isn't twice a natural number, I can't do that, so it's much less clear how to proceed. But if I can get down to the order product, then I'm much happier, because if I have an exponent 2q up here somewhere, it passes through the order product very nicely, so I just get an exponent 2q here. And then if I write this as an exponential, it just becomes a 2q as a coefficient in the exponential. So I'm much happier handling fractional powers, or not twice integer powers, with products than with sums. So that's one reason. Another reason, so in the order product, these terms, 1 minus f of p over p to the s to the minus 1, are independent, which is always good. Yes? Yes, thank you. Yes. Right. So in the order product, these things are independent, which is good, whereas in the original sum, the independent f of p's are all sort of tangled up, making up the f of n's, which is much harder. And then the third reason is, I already told you, so on the 1/2 line, the order product is responsible for the drop-in size as compared with square root cancellation. So I've told you we're going to have a drop-in size here as well, so maybe the order product is going to be a useful thing to have around. Yes? Here? Right. So I said here. So the size of the first moment is smaller than you would expect just from square root cancellation. The reason it's smaller is because this thing doesn't behave like this sum, it behaves like the order product instead. The order product doesn't converge, but it still governs the size, despite not converging. So it requires a lot of work to see that it still governs the size, but heuristically, that's why this is the size. If you pretend that this is like a random order product, this is the answer you would get. If you pretend it's like a random sum, this is the answer you would get, which is wrong. Okay. Other questions? Right. So I want to get the order product into play. How can I do it? So the obvious way is to use Perron. Okay, so sum of f of n is like 1 over 2 pi I, the integral up a line. And f is a finite product, so I can have any positive abscissa if I want to. But this won't work, so why not? So this is inefficient. Well, first of all, I have this 1 over s around, which isn't very good because I'm probably going to end up putting some absolute values inside the integral at some point. And then I'll have something like integral 1 over mod s, which diverges logarithmically and that's a disaster because I'm trying to wing square root log x at most. So if I lose a log, I'm done. Now you could fix this if you were happy with having a smoothly cut sum instead of a sharp cutoff here, which you might be. But then there's a much worse problem. So first of all, that diverges logarithmically. Also, we would need to get cancellation from the oscillations of f of s times x to the it, which is generally very hard. Okay, so if I took c to be 1/2, which is the most natural choice, then I'd have an x to the 1/2 here, which would come out, and that would give me the x to the q in the answer. I take the 2qth moment. And then I'd be left with an integral, and what I'd be trying to show about the integral is not that it's smaller than a small power of a log, or even that it's bounded. I'd be trying to show it's actually small. It's going to 0 like 1 over root log x. So to possibly do that, I need to show that there was lots of cancellation going on in these guys, which is very hard. So I'm going to say just a little bit about another way of proceeding. So instead, I'm going to let P of n be the largest prime factor of n. And what I could do is I can decompose my sum according to the size of P of n. So I'm going to split it up to the numbers n, where P of n is at most x e to the minus k, and at least x e to the minus k plus 1. And then I can split up this sum, so every number here has at least one prime factor on this range, and none which are bigger. So I can split these numbers up into the piece which has all of its prime factors on this range, and the piece which has prime factors smaller than this. And since f is multiplicative, when I do that, f will split up over these two sums. Okay, so this is the same thing as the sum over k bigger than 0, the sum over m less than x, such that if p divides m, then p is on that range. M strictly bigger than 1. F of m, and then the other part. So the sum over n less than x over m. N is x e to the minus k plus 1 smooth. F of n. And the important thing to note here is that in this sum, we only have prime factors up to x e to the minus k plus 1. And in this sum, we only have prime factors that are bigger than x e to the minus k plus 1. And those things were chosen independently, so this is independent of this as a random variable. So we'll come back to that in a minute. So by Holder, if I have just some coefficients, some numbers, Cm, and we'll call this here I sub k, this interval. So if Cm are just some numbers, and I look at what's the expectation of the sum over M with all of its prime factors in I sub k of f of m Cm to the 2q. Well, by Holder, this is at most the expectation of the square of that sum. All to the power q. And then for the square, I can just expand that and use orthogonality like usual. So this is the sum over m with all its prime factors in I of k, mod Cm squared to the q. Right, so this is a little calculation. And this is true if the Cm are some deterministic numbers. But the point is that since the sum on the inside there is independent of all the randomness on the outside, I can condition on the sums on the inside and treat them as deterministic. Okay, so by conditioning, if I call lots of lines here now. So if I call this whole double sum here S sub k, thing on the inside there, if I look at the expectation of S sub k to the 2q, I can do the same thing, and I can get that this is at most the expectation of the sum with the prime factor condition, and then just treating the sums up there as deterministics, as a deterministic coefficient. So the sum over n less than x over m, n is appropriately smooth. F of n squared to the q. Okay, so if you're not used to this, you can just think, since I have this independence, I can freeze the things on the inside. Then I can do Holder, like in the deterministic case. Then I can re-randomize over the things on the inside. That's what happens. Or I can split the expectation up into the expectation over the inner thing, which is here, and the expectation over the outer sum, which goes away in the Holder application. Right. Now, once you get to this point, you then do a few more steps, which I'll just list what they are. So now you can replace the sum over m by integral. Okay, and when you do that, you pick up a weight that reflects the density of the set of numbers that you're summing over there. And once you've done that, so you then have, inside the bracket, you have an integral of the square of some sums at various points. So an integral of a square of some things looks a lot like the kind of thing you could hope to apply Parseval to in some form. And you can do that. So then you can apply a suitable form of Parseval, and when you do that, so on the physical space side, you have a sum of f of n. On the frequency side, you have the Dirichlet series or the Euler product, which is what you want. So when you apply Parseval, what you finally get out, so of course I'm omitting a lot of stuff here. So you get that this is roughly the same as x to the q times the expectation 1 over log x, a short integral, so from -1/2 to 1/2, absolute value f of 1/2 plus it squared dt, all to the q. Remember that this is a finite product here. So if you've seen these kind of things before, maybe you can vaguely follow what happens in the steps I skipped. If you haven't, then you're definitely not supposed to be able to follow what happened in the steps that I skipped. Point I want to make is, why does this work? So why does this overcome the problem that I was talking about over there? So there, I had this x to the it around. I needed to capture some of its oscillation, and I didn't know how to do that. Here, I use Parseval. In Parseval, there's no oscillation. Okay, in Parseval, you have a mean square of something on one side, and you have a mean square of something on the other side. So there's no oscillation that's being lost because there was never any oscillation in the first place. And you might worry that this holder step here is wasteful, but it's not, because in particular, if you look at the case where k is 0, which is one of the terms in the sum, then the sum over m, it's basically just a sum over primes, so just independent random variables on the primes. And when you have a weighted sum of independent random variables, then this holder application is going to be sharp by Khinchin's inequality, which gives a low bound. So nothing has been wasted in this argument. And you've bypassed having to control any sort of oscillation in the integral, and you get, well, actually not that, but something that you could pretend is like that as the answer at the end. So now, to prove the upper bound in the theorem, what we want to show is that the expectation 1 over log x, integral -1/2 to 1/2, f of 1/2 plus it squared dt to the q is less than 1 over root log x to the q. If q is strictly less than 1. So do I have about 8 minutes left? Something like that? Yep. Okay. So, right. So I'll say a tiny bit about this, but I won't try and go into any details at all because I think it would just be too confusing to try and do that in the time that's left. And then after that, I'll say a little bit about how you can transfer this to the deterministic setting. Okay, so a tiny remark about this. So if I take q equals 1, what happens? Well, if q equals 1, then the expectation and the integral can be swapped. So I get 1 over log x, the integral from -1/2 to 1/2, expectation f of 1/2 plus it squared dt. And this expectation is like log x in size, like the second moment of the zeta function or L function. So this thing is order 1. Okay. As I said, this is order log x. And now we're back to the sort of discussion at the very start of the talk. So there are two ways that the expectation could be order 1. One way is if typically thing in the bracket were of size about 1. It weren't often very much bigger than that. And another way is if usually the thing in the bracket is smaller than 1, but there are a few large values which sort of inflate the expectation. And what we need to figure out is which of those is going on. And if the answer were that it were typically of size 1, then the answer on the right-hand side would be 1. And if the answer is that it's typically smaller than 1, then you can hope to get some saving. And the answer is that it's typically smaller than 1. Right. Maybe I can say one more thing about that to try to vaguely satisfy people who are interested. So to do this, what you need to do is you need to think about is it true that 1 over log x times this integral is roughly the same as 1 over log squared times the sum f of 1/2 plus I k over log x squared. So that is essentially true because this is like the Riemann sum for this integral when I split up on a scale of 1 over log x. But is it true that that's the case with the different things in the sum? So with f of 1/2 plus I k over log x being roughly independent of one another. So there's a usual kind of heuristic that when you have an Euler product like this, it sort of renews itself on a scale of 1 over log x. So when you move by more than 1 over log x, you start seeing different behavior. So there's a usual heuristic, which I'm afraid I don't have time to explain for people who haven't seen it before, that this should behave roughly like that thing with these things being sort of independent. But in this problem, the answer to this is no. So they don't behave roughly independently for the purposes of this problem. This is ultimately where the 1 over root log x comes from. Right, now rather than trying to rush and say something incomprehensible about that, I'll finish with a few remarks about the second theorem, the deterministic theorem. So the deterministic case right, well, first of all, there was this quantity L, which was the minimum of x and r over x. Where does that come from? Well, that comes from what, depending on your predilections, you might call the approximate functional equation or Poisson summation, or the Polya Fourier expansion, or various other things. Okay, so we know that the sum over n less than x of chi is roughly the same as the sum over n up to r over x of chi times a certain prefactor, which is that. So if I had square root cancellation in this sum, I get square root r over square root x, and it would partially cancel, and I'd get square root x, so I'd have square root cancellation for this sum. And if I can get a bit more than square root cancellation in this sum, I can get a bit more than square root cancellation in this sum, but my saving will only be on the scale of r over x rather than x. Okay, so this is where this comes from. We know there's this symmetry between x and r over x. This is also why the Montgomery Vaughan upper bound that I showed you earlier is true. If I have x being really close to r here, this sum is just a bounding number of terms, and everything is just controlled by this deterministic piece here. That's why they get this uniform r to the q upper bound. Right, and the last thing I'll say, so in theorem 1, we conditioned on these primes f of p for p up to x e to the minus k. Right. So this is lots of primes to condition on. So for example, when k is 0, this is all the primes up to x to the 1 over e, power of x. So I can't really hope to do anything like that for Dirichlet characters. But the reason that we conditioned on all those primes up to x e to the minus k was because we wanted a sharp result in the random case. If I just want some result, which is better than square root cancellation, which for the moment I'd be happy with in the deterministic case, then I don't have to condition on all the primes up to there. I can just condition on some of the primes and leave the others to be taken care of by holder. The holder argument always gives me like square root cancellation, and any primes I have left and didn't put into holder, I can hope to win something from. And this is how the argument works. So in the character sum case, just condition whatever the arithmetic version of conditioning is. So just condition on the values chi of p for p up to about, let's say, log r to the 3/4. Now I can do that because I have log r to the 3/4 conditions, so that will maybe give me, will cut down the size of my space by something like that when I do the conditioning. So I have that many conditions. I have r minus 1 characters. This is much bigger than that number. So if I have much more characters than I have conditions, I can hope that I'll still have a lot of characters left in each little box after my conditioning. And this will be enough to win something. Okay, so I think that's probably a lot to have said, so I'll stop there.
Thank you very much, Adam. That's a lovely talk. Do you have any questions?
Do you think that for the character sum estimate, your exponent would double log to the minus q over 2? Do you expect that to be optimal or not?
Yeah, so I think that, so in the character sum result, there was this minimum square root log log L, square root log 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 R. So I think if you could remove the square root log 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 R, which I think is maybe possible, then that would be an optimal upper bound. That would be the analog of what you get in the random case, except for taking account of this symmetry between x and r over x.
Wouldn't be the analog of what you get for first mean of L half chi?
No. So in that case, you save log to the 1/4, I guess, over the square root cancellation. Here, you're saving a lot less. So I don't know how to prove lower bounds in the deterministic problem, the character sum problem. But if you believe that but I do have a lower bound in the random case. So if you believe that the character sum problem is like the random case, apart from the symmetry between x and r over x, then that would be the optimal upper bound.
Any further questions? Do you think about what might happen if you
So it shouldn't make any difference. So I said,
Resuscitate the Perron's formula approach?
no. So as I said, there are two things that go wrong in Perron. One is the problem with the 1 over s weight. This would go away if you had a smooth weight. But there's also the problem, so it's essentially you want to wing a 1 over log x somewhere. So the size of f of s, the product you're sort of expecting is like log x. So you want to wing a 1 over log x to kill off most of the size. In Perron, you've never done that. You just have an f of s around somewhere. The reason for that is because you have this oscillating x to the it, which should give you some extra saving, but it's very unclear how to capture this extra saving.